In this video, I'm going to talk about an extremely important idea in statistics, which is called the normal distribution. And to explain it, I'm going to use this app that I've developed. You can find the link up here. So, what is a normal distribution? Well, it means that you have a variable which can have different levels. So, you roll a dice and you can have different results for when you roll a dice. And then you can look at the frequency of getting different levels of a variable. So the different frequencies of getting different numbers on a dice, or the different frequencies of seeing different heights for different people, or levels of extroversion or blood pressure and so on. You have some variable on which people differ. A normal distribution is when the most common value is the mean, the average, and then the further you move from the average, the less common it becomes, the lower the frequency becomes in a characteristic bell-shaped pattern. And you can see it in a histogram. So here we have the sum of dice rolls for a game. So what this app does is it simulates dice rolls. Let's imagine that you're playing a board game such as Monopoly or Cluedo or Frustration, and you roll the dice and then you add up the numbers on the dice and then you move that amount. How many do you move? And what it does in the histogram is it tells you, well, how frequent is each level of the variable. So you can see it in a histogram. It's not normally distributed here, but it will be later on. And you can see it either from a histogram, or you can test for normality with the Shapiro-Wilk test. So if the p-value is less than 0.05, then the variable is not normally distributed. Here it's not normally distributed. But if it's 0.05 or above, then the variable is normally distributed. So let's start here. What we have in this app is it simulates dice rolls, and then it adds up the scores for all these different dice. So you can change the number of dice that you roll. So the number of times you roll the dice. So I could have one dice that I roll 100 times, or I could have 7 dice that I roll 100 times. The amount of turns that you have essentially. Then we have the number of dice that you can roll. So here I'm rolling 2 dice, and also the number of sides of the dice, because you could imagine a 2-sided dice, a coin, or sometimes people play these fantasy games, the Dungeons and Dragons stuff, where they have 20-sided dice. But let's imagine that we have a single dice with 6 sides and we roll it 100 times. Well, what we tend to see is the distribution is very flat, a very flat distribution. It's not normally distributed. This is called a uniform distribution. A uniform distribution is where every level of the variable is equally likely. You're just as likely with a single dice to get a 1 as a 2 as a 3, etc. But let's say that we change the number of dice that we roll. Now we've rolled 2 dice, and the pattern's a bit different here. What we see is, well, things are a bit more common around the 7 and not much around the 2. Let's try a few more dice, because the rule is that as the sample size increases, the closer the sample comes to approximate the actual levels in the population. So in the case of dice, the more times we roll the dice, the more turns we have and we record, then the closer our probability of getting a particular, the closer our frequency in the sample becomes closer to the actual probability. So let's imagine that we roll the dice more times and more times and more times to 1,000 times. We can see it actually starts to look a bit more normally distributed. So the rule is the more times we measure our variables, the more normally distributed they look. So what we have, 1 dice, flat distribution. It looks a little bit different every time because it's simulating random numbers. But for 2 dice, it's more common in the middle, looking more like a normal distribution. And the reason for that is if you have 2 dice and they're independent, so the roll of 1 dice doesn't tell you about what you roll on another dice. They're separate statistical events. what happens is if you add them together to find out the score, then there are going to be more combinations that are going to give you a 7. There's only one combination that can give you a 2, that's a 1 and a 1. There's only one combination that can give you a 12, that's a 6 and a 6. There are actually 6 combinations to give you a 7. And so, well, the more predictors we have, the more dice we have, then the closer our distribution comes to looking like a normal distribution. So we could try that with 9 predictors, we could try it with 20 predictors. There you go, it's looking a bit more normal. Actually, in this case, it is a normal distribution if we look at the Shapiro-Wilk test. And so, the more predictors a variable has, the more it looks like a normal distribution, because each predictor has different levels, and more combinations of those levels of the predictors are going to be in the middle. So let's imagine we have thousands of genes which predict height, or thousands of genetic differences that predict height. It's very unlikely that you'll have all of the genes for low height or all the genetic differences for high height, but you'll probably have some of both, and maybe you have half of one, half the other. Someone else has half of one, half the other. There's more combinations that's going to put you in the middle. So if a variable has a lot of predictors, it's going to be normally distributed. A lot of variables in psychology are normally distributed because they're just predicted by so many things. By genetics, by social factors, by behavioral factors, the physical environment. A lot of things in psychology are predicted by huge numbers of things, and therefore they tend to be normally distributed. It's also the case that whether our variables look normally distributed depends on our level of precision in measuring the thing. So let's imagine that I was performing some analysis and I want to find out about a predictor of an outcome. Let's say we're looking at psychological health, and one predictor could be income. Well, I could say income could just be high or low. It's a two-sided dice, a coin, or I could have a high level of precision. I could measure it from 1 to 10 or 1 to 40 or the actual number. So the rule is that if the predictors have fewer levels, well, that doesn't look normally distributed. But if the predictors have more levels of a predictor, so the more levels there are of your predictors, the more combinations there are going to be of different levels, the more it's going to look normally distributed. So to summarize, larger sample, more dice, more predictors, larger sample, more turns, more predictors, more dice, and more precision. All of those lead to a greater normal distribution, and we can put that all at the top here, take it all to the limit. Very high levels of all three, high precision, high number of predictors, and large sample. That, my friend, is a normal distribution. We can see that with the Shapiro-Wilk test, and we can also add here overlay with normal distribution, and we can say yes, it is normally distributed. Wonderful. And so that's where the normal distribution comes from. Lots of predictors with lots of different levels, in lots of different people, with lots of combinations, most likely giving the mean value. So what I'd like you to do is I'd like you to have a little bit of a play around with this app and see which levels of these three different parameters are necessary to come up with a normal distribution. And so, well, so that's our introduction to the normal distribution.